Yeah, thank you. Thank you so much. Thank you so much for letting me come and join and give a talk. I signed up kind of last minute, but I appreciate it. And this has been super fun so far this morning. I've enjoyed all the talks. I don't know in 5 minutes if I'll do scaling laws, but I'm at least going to just like sketch a high level thing about infinite width limits and infinite depth limits and try to move from just standard vanilla MLPs all the way up to kind of modern mixture of experts transformers. So that's the goal. So it's going to be a very architecture focused talk. But first, just at a high level, like, this is an interpretability workshop. I mean, there's a lot of excitement right now in AI. Like all of the modern models are really revolutionizing code generation, language generation. There's excitement about protein folding, predictions, self-driving cars. Like if you've gotten a Waymo recently, that's all driven by object detection and segmentation. And you can make fun graphics, right, for your talks. That's great. Okay, what is the kind of like a harsh reality about this trend of recent models is that so there's driven by this observation that there's a consistent return to performance by increasing the amount of data that you train on and the size of your model. These are summarized by these sort of neural scaling laws, which hold across a bunch of different modalities and domains and model types. This has led to investment in much larger models, right? And the scale of the sort of frontier pre-training runs is really kind of astonishing. So as an example, so like last week there was this release about this Claude Mythos model, right? And apparently it is a 10 trillion parameter mixture of experts model. Okay. Does anyone know the cost of the Artemis 2 launch a couple of weeks ago? Does anyone know, like per launch, how much does this cost? It's about $4 billion. Yeah, that's right. Yeah, $4 billion. The cost of Mythos pre-train, like the pre-training run to get the 10 trillion model, is about $10 billion US, right? So these modern pre-training runs are literal moonshots, right? So these are expensive. We need to kind of like understand what's going on. We need to try to make them stable and predictable. Okay. So that scale is a kind of engineering challenge, but scale also presents a challenge to people who want to understand what these things are doing and try to interpret them. So there was an idea in like, the first couple of talks mentioned sort of the kind of history of some of these interpretability approaches. One idea that's people have thought about in neuroscience, but also in kind of the context of AI research is, can we map single neuron responses? Can we try figuring out what single neurons do? Do they have kind of very selective properties? Could we maybe map circuits? Could we maybe identify what a given induction head does? This is challenging at a large scale model. So let's say we took this Claude Mythos thing that they just trained. So there's going to be like 3 million parameters in the residual stream, or 3 million neurons in the residual stream. Categorizing each of them, trying to find which of the many things in the language data set they respond to seems challenging. There's also kind of a philosophical question. So like does or should a theory of deep learning tell me about what a given neuron in some layer or what a given attention head and some other layer actually compute? I mean, that might be too challenging. If you go to the Anthropic kind of, the transformercircuits.pub site, on one of their blog posts, they have this kind of atlas. It reminds me a lot of the brain, like the Allen Brain Observatory Atlas, where you could look at what neurons and visual cortex respond to. So they have that for certain neurons in their one of their trained models, like the Sonnet model or something. And they try categorizing, so this neuron has a auto-interp score of 0.162, and like the claim is it responds to negations like don't. And then here are some examples where it does that, and some examples where it doesn't. They have other neurons that are, okay, so this is one idea, which is like maybe single neurons do specific things. But there's this problem that is common in neuroscience and also in deep learning, which is that single neurons actually might be like polysemantic or mixed selective, depending on your background. They might respond to multiple types of inputs, and maybe the unit or neuron basis is not the right basis to interpret the activity. And depending on your favorite tool, maybe you do representational similarity analysis, or you think about object manifolds, or you think about sparse autoencoders. So there's some maybe latent space, and you're doing some kind of computation in this latent space and trying to carve up the latent space. Okay. So that scale is a challenge. I want to give a different perspective of scale as an opportunity. So scale as an opportunity is something that a statistical physics person would like. So large systems can sometimes be simpler than small systems. So a system with infinitely many particles, for example, could be described by some macroscopic laws, like the ideal gas law. You can summarize things with phase diagrams. So who knows the Hopfield model? Does anyone? Yeah, okay. So in like the 80s, some physicists worked out the phase diagram for the Hopfield model. So it's a function of the number of memories you're trying to store divided by the neuron count and as a function of the temperature, so the size of the thermal fluctuations, you can categorize whether you're going to stably retrieve a memory, whether retrieval is sort of metastable, whether you have a spin glass phase. So you can carve up kind of the space of possible behaviors. And there's a similar thing for just supervised learning in shallow networks performed by Elizabeth Gardner. So, when can you, for a random labeling of all my data points, always find a separating hyperplane versus not as a function of the number of data points compared to the dimension of the space. So there's sharp phase transitions in high dimension that you can characterize with statistical physics. And the infinite system is easier to characterize than the finite system. And from some of these sort of toy models of neural networks, and especially simple kind of neural network models from the 80s, there was this picture that maybe the collective network properties, like averages over the neural population of certain things, actually govern the kind of predictions that the model performs and govern the kind of performance or the generalization or the capacity of the model. And single neurons instead may be acting more like particles. So they might each provide a small contribution to network averages. They might have some kind of complicated statistical description that is mixed selective and random. But we only care about averages over this distribution. Okay, so that's the mean field picture. Okay, but modern architectures are not like those models that were analyzed in the 80s. They're really complicated, right? They're multi-layered. They have all these different kind of structural components. There's feed-forward networks. There's convolutional networks. There's attention networks, transformers, these sort of self-attention modules. Okay, how do we make progress? So the key question I want to ask in this talk is, are there cases where we can say something about how these models behave as they become very large? And also, on the way to that question, you have to tell me what you mean by large, right? So these different modules have different scaling axes, and you could decide how to make them bigger, how to increase the parameter count. Another question you might be interested in is understanding at what scale or at what model size or amount of data that intelligent behaviors emerge, right? The ability to code or or write a haiku or something. So whatever you want the language model to do. Okay, I'm not going to answer those questions. Those are just kind of high-level ambitious goals. But in today's talk, I'm just going to discuss basically a couple of very simple architectural limits that we can understand. We'll start with just width and depth limits of MLPs. The story that I'm going to tell is basically about what I'm going to call a dynamical mean field theory. So the idea is that if you take an infinitely large network and you randomly initialize all the parameters and you take the width to infinity, the neurons decouple. And they behave as sort of independent particles. And they only talk to each other through population averages, which become deterministic in the limit. And then I'm going to try to move from this architecture toward, our most recent work was on a sort of mixture of experts model, where there's kind of some rich and interesting structure. And then I'll try to discuss one practical application of doing some of this stuff, which is sort of hyperparameter transfer. Okay, cool. And I think I'm not going to get to neural scaling laws, but I think Cengiz might discuss neural scaling laws in his talk later in the week. Okay. So let's just look at this neural network. So this is just an MLP. So I take my data, I go through a linear layer, I apply nonlinearity, linear layer, nonlinearity, linear layer. I do that L times, and then in the last layer, I just take a linear combination of the last layer features. And I get a scalar. Okay, so I'm going to start all the weights as sort of random at initialization. You could change it. It doesn't have to be standard deviation 1, but I'm just going to take it to be 1 for this talk. And because you start at a random initial condition, the initial prediction of the model is maybe wrong. Maybe it's cat when the right answer is dog. And then what we do is we don't just stay at this random initial condition. We want to update the parameters. So we go downhill. So for example, we could do gradient flow or gradient descent or something. Momentum, atom, pick your favorite optimizer, and you flow downhill in this sort of error landscape. Okay, cool. And the question is, can we predict or summarize what the model learns in some appropriate infinite width limit? Okay, so the first thing I want to say is, okay, so notice there's this little gamma parameter. So if you've read, the Shazat and Bach paper on, lazy and rich regimes of training, this is related to that. So I'm going to start with just a width 64 ResNet. So it's just a CNN. And I'm going to increase the width with gamma constant. So I'm going to do that first. So this is known as the NTK parameterization. So this is one way of scaling up the width of the model. And it has a well-defined stable infinite width limit. But what's interesting is when you go from 64 to 1024, the training dynamics slows down. So you're spending more money per step because it's a bigger model, but you're getting actually worse performance. So that seems weird. But if instead you do gamma like square root of n, which is known as the mean field or mu-p scaling procedure, notice now that all the sort of training curves more or less collapse, and if anything, the wider networks are better. Okay, so this is just to say that there's different ways of scaling up. It kind of matters which one do you pick. This is one example, and we're going to have other examples. Okay, cool. So the proposal is we want to work in this kind of regime, where instead of approaching the NTK limit, we want to approach this other, what I'm going to call the mean field limit. Okay, cool. So first, let's talk about width. And to kind of characterize some kind of asymptotic description of the network in this limit, I'm going to need an idea from physics. So I'm going to just describe at a high level. In a simple example, what DMFT or dynamical mean field theory is. Okay, so imagine I just have like a coupled dynamical system, and let's just take it to be a linear system. So I have this Jij matrix that's sort of a random coupling between all the sites. It's going to be random and symmetric. And then I could have some time varying, regularization that keeps me on the sphere, for example, if I want it to be a spin glass. And my claim is if I have these random couplings, so symmetric random couplings, if I take the infinite system size limit, this system is actually equivalent to a one-dimensional system. It's a one-dimensional system where it takes in a colored noise process, eta of t, and then computes some kind of like integrated response against itself that encodes kind of its interaction with the rest of the network. Okay. So one way of viewing this is that the dynamical system, or the right-hand side of this differential equation, can be replaced with a colored noise process and a memory term. So the cost is you go from a Markovian system that depends on some kind of random couplings to a one-dimensional stochastic process that is non-Markov, but you can compute everything from just this one-dimensional process. So you trade high dimensions for Markovianness, I guess. Okay. And from this single site picture, you can actually think about S as a random variable, where the randomness is describing the statistical properties across the sites in the network of this S variable. And to do population averages, it's actually the same as averaging over this colored noise process on the right-hand side. So you could compute the correlation and response function from this one single site dimension. Okay, cool. We just did that. Yeah, so how can you calculate this? So if you're interested in, if you know path integrals, or it's basically a fancy moment generating function approach to this problem, you can identify the correlation response function from an appropriate saddle point that holds at large n. There's a cavity method argument where you imagine adding one new site to the system, figuring out how it interacts with all the other sites, and then marginalizing out the kind of interaction in a meaningful way, and that gives you this extra response term. And then if the dynamical system is linear, you can kind of actually just directly apply kind of random matrix theory ideas. And you can map the kind of correlation response functions to certain properties of random matrices and free products and things like that. We have a sort of a review that you could check out. And if you look, so you could look at this recent thing, or if you're in the Boston area, you could ask Francesca, because she's an expert on DMFT things. Okay, cool. So my claim is the following. So if you take an infinite width limit of this randomly initialized network and train it with SGD, you can instead think about, for every layer of the network, a two-variable stochastic process. One variable corresponds to the forward path to the network, one variable corresponds to the gradient through the network, and these two things are coupled, but they're both driven by Gaussian noise, and then they integrate some kind of non-Gaussian correction through a response. The gradients are what you do through back propagation, so it's the derivative of the output with respect to one of the hidden states. Okay, cool. And my claim is that the entire kind of, inductive bias, whatever you want to say, the computation that's interesting in the network, everything at the network level, the macroscopic level, is governed by what I'm going to call dynamical feature kernels. So for like a layer L in the network, I ask for two different pairs of inputs, XX prime, and two different times of training, TT prime. This is the correlation of the hidden states, phi of h, at those pairs of data points and time points. And the corresponding thing for the backward pass kernels as well. So if you, okay, so those two things are kind of clear why they would happen. And then from this like interesting average over the weight matrices, there's two other objects that show up, which are these response functions. So if I kicked the R variable, what does it do to the H variable at a later time? And if I kicked the U variable, what does it do to the G variable? Okay, fine.
This is
Well, okay, so this is not, yeah, so this equals, I guess, implies concentration. So at finite width, all of these objects, A, B, phi, and G are random variables. And the equations that I'll write down are true. Okay. This equation is true, conditioned on phi and A and all of that. But the problem is phi and A themselves at finite n are random variables. So you could do a perturbation series as you described, where you treat them as like there's the limit, and then there's like a 1 over square root of n central limit theorem correction, and then like a 1 over n bias correction. You could work out kind of corrections, but this sort of holds conditional on the values of those.
Right. So what I think is like the free energy at finite width decouples. So like has a simple expression if you condition on this kernel.
Right, and where this comes from is sort of you've averaged out all the kind of randomness from the initial condition, and that produced basically this extra Gaussian. So if you know neural network Gaussian processes, that's this sort of term. And then if you know, this comes from the DMFT response that you got from averaging.
No, I'm saying like, at finite width before you have a Gaussian process, it's like up to gauge this is a complete invariant. Well, whatever. I think that's right.
Yeah, we could let's chat after. I'm not totally sure, but I think so. But my point is just one thing I just want to stress is, so you have a factorization. So across the neurons in each layer, you have a product measure on the activity of the neurons. You can think about this as a histogram of the activity across slices of time or on different data points. And the formulas are not important. The point is I just want to say, just like the example I gave, there's a colored Gaussian noise process that drives the right-hand side and a feature learning non-Gaussian correction. Okay. And if I know that, okay, so this is what I mean by the macroscopic behavior of the network is governed by these phis and g's. So in gradient flow, so you can also work out discrete time or SGD or other things. I'm just writing gradient flow so it connects to the NTK. Basically, this is the NTK, the sum over layers of GL plus 1 phi L. But it's an NTK that evolves through time. And so if I know the phis and g's through different steps of training time, then I know actually the behavior of this NTK through training time, and I know how the function evolves.
What is delta?
Oh, yeah, okay. So delta is the prediction error. I didn't write it down, but it's basically the derivative of the loss on that data point with respect to the function on that data point. So for mean squared error, it would be like the target y minus f. But for a different loss function, like cross entropy, it would be like d cross entropy df, something. Yeah. So. Okay, cool. Yeah.
Do you have to worry about non-perturbative effects when in n?
Non-perturbative in n. It's an interesting question. So I'll try to discuss some what we know about finite size effects near the end. But it's a good point. Yeah, and what this theory will capture is basically a little bit too optimistic in the sense that you're throwing away any like scaling law effects. So when you train models of finite size, you sort of are close to this infinite width behavior for some period of time, and then after some period of time, you sort of start plateauing in performance. You sort of saturate. This will not capture the saturation effect. This theory doesn't. Yeah.
Does it have to be like necessary like a finite width effect, or is it just like some instantonic correction or something like exponential of y minus 1 over n would be something that goes to.
Oh, so I don't think it has that structure. Okay. So you're worried about like e to the 1 over.
Non-analytic stuff.
Yeah. So the action is analytic. Everything's analytic in n. It's well behaved. Yeah. But so it is like just a typical like Laplace kind of expansion. Okay. Or yeah.
You can get instantaneous, but you can get rid of instantaneous if you have bounded activation in some sense.
Okay, so I mentioned that there's this scalar that so just like in the Shazad and Bach papers, right, there's a scalar variable. My point is that this scalar variable that controls how lazy or rich your training is, that persists even if you go to this infinite width limit, and you can vary it from like small-ish, so like 0.2 or something, make it really large. And the point is, I'm just saying it sort of deforms the dynamics. You see that there's more non-Gaussianity in the hidden states, but you also kind of accelerate training as you go to this like higher feature learning, higher riches. And the other interpretability kind of thing, so this is just a two-class classification problem, very simple toy example, but you can see that as I go to this larger feature learning strength, you're getting like more and more clustering by class, right? So you have these 2x2 kind of class structure. So within class similarity is like higher than a between class similarity. Okay. So the lazy limit is that you take this parameter gamma 0 to 0, right? And this is sort of like what would happen if I kept like going to larger and larger width. Eventually that would approach some kind of limiting curve. And if I train for infinitely many steps at infinite width in this lazy learning limit, that is very easy to define what it does. It actually is a minimum norm interpolator for a given norm that's defined by the initial NTK of the network. In some sense, theorists like this. It's very kind of analytically convenient, but it misses out on sort of the deep learning component of the deep component of deep learning, right? So it's basically reduces this to, you have your input data, you go through a static feature map, and then it's like you're doing some kind of linear method, like linear SVM or linear regression in this this feature space. Okay, so that was all about infinite width. Can we say something about scaling the depth or scaling other architectural variables? So in general, for a general feed-forward network, I think it's still an open problem. You might need to do like shaped activations or things like, if you know Muffon's papers on those things. But the case where we've made the most progress is on residual networks. And fortunately, most modern models are residual networks. But basically what I'll describe now is, so imagine you have a residual network like this, where each block is like block depth 1. So I take the H, and then I do a linear layer, and then I add that back. After a scaling factor, I add that back to H, right? So there's a skip connection, and then a learnable component. And my claim is for any alpha between 0.5 and 1, there's some kind of limit at large depth. And the result is a kind of DMFT or a dynamical system that holds across the training time and across the layer time. Okay, so here's the claim. So let's start with the SDE limit. So like 1 over square root of L is the prefactor. So the claim is that there is a joint limit for width and depth that's kind of commutative through training time. And all the order parameters, so all the feature kernels and gradient kernels that are defined that govern the network behavior approach this kind of a deterministic limit. Okay, and to get some intuition, let's think about what happens at initialization. So just think about the W's as random and before a step of training, for example. So before training, let's define the average, so the variance across all the neurons in a layer is HL squared. And so this just has a simple recursion. And you can see that at the level of the variance, it's basically, the update between layer L and layer L plus 1 is of scale 1 over capital L, the total number of steps. So it's like an Euler discretization of some kind of ODE. And the NTK object is an average over all the layers, which as capital L goes to infinity will turn into some kind of integral. So there's some kind of well-defined continuous time limit where time is current layer index over total layers. Okay. And yeah, so you can define this tau as the layer index over all the layers, and then you can write down a similar expression for the DMFT through training time. So there's a training time t, layer time tau, and like the data x prime. So this would be the kind of gradient flow expression in this resonant.
You use some stability property, right? Like in the EDOT, or can you just do this with any nonlinearity activation?
Oh, okay, good question. So these response functions are not well behaved if, I think you need at least 2 derivatives of your activation function for these variables A and B. These response functions will actually be not well defined if I think your second derivative doesn't exist for your activation function.
If your, for example, your initialization is off by kind of one factor, then like in like principles of deep learning theory, there's this phenomenon that happens where you blow up exponentially. Does this not happen here?
I'm not sure. So what is the problem? So under what condition on the activation function?
So at initialization, you have
Yeah.
kind of explosion.
Okay. I think there probably are exotic like activation functions that would cause the concentration to break down. But I think for in this expression, right, anything with like, I would imagine any like 5H with bounded sort of second moment like this would be fine. So certainly if you choose anything analytic like tan H or something, you're fine.
Yeah.
Or the swiggloo we saw this morning, or things like this.
Sorry, rather basic question of how do you see that the CLT, how do you see concentrations for these quantities?
Yeah. So you can get it a couple ways. So one way is like a formal derivation is you can write this whole thing as like there's a moment generating function for, let's say, the outputs of the network, and you can show after averaging over all the weights that it has the form e to the minus n times some order 1 function that depends on all these order parameters. So basically all the order parameters satisfy a sort of steepest descent or like large deviations kind of property. And you get the equations I'm writing down are the saddle point equations that you would get. So it's what you'd get at like the lowest order of the theory. Okay, so one thing based on, there's some great work by Greg Yang and colleagues on this idea of, okay, so if you nail down a parameterization so that things are roughly consistent across model sizes, there's hope that you might not have to retune all your model hyperparameters as you go from a small scale model to a large scale model. So for example, I could find good learning rates in like a small width model and then jump to a larger width model and the same learning rate would work, or a large depth model. So for example, here I'm showing a case where the width is controlled but the depth is not controlled. And so as I go from a depth 6 model to a depth 30 model, the missing dots are runs that diverge. So you can see that the good learning rate in the depth 6 model is not a good learning rate for depth 30. So that's the case of not transferring. But then if you do this like mean field theory scaled branches thing with the 1 over square root of L, things line up a lot better. So I can jump from like a depth 6 with with 128 model to like a depth 30 with 1024 model, and it has the same kind of stability conditions. So the max learning rate is still the same. And this, yeah.
What's the difference between this method and UP?
This is mu p plus this depth scale factor. So I'm on the residual stream. I'm doing 1 over square root of L or 1 over L, depending on the setting.
Yeah, and I guess like what architecture is this?
This is right now. This is a CNN.
Okay.
Like a ResNet. Okay, so now I want to move on to kind of mixture of experts transformers. So this is like what most models these days are. So you alternate between multi-head self-attention on the residual stream and then an MOE model. So it's a special type of MLP layer where you're activating sparse subsets of the network. And so the attention block, we've heard about attention today, but you have in a multi-head attention model, you have multiple heads. There's a size for each head. I'll call that NH. I compute key query inner products to get these attention variables, and then I weight the values by the attention variables and then map back to an output space that's n-dimensional. So that's the residual stream dimension. And mixture of experts blocks are similar. Instead of these like attention variables that are gating the values, here I have basically a sparse top K router. So I activate K out of E experts. So I have E experts and K of them will be active. And then I will basically compute some kind of combination of these active experts to generate the output back to the residual stream. Okay, cool. So first thing that we did was, so the analysis I gave you for depth scaling was based on this like, each block was one layer, right? So it was like W times phi of H. But these are kind of complicated there are multiple parameters within each of these blocks. So, even though there is a well-defined feature learning limit for any alpha, any depth scaling exponent between 1/2 and 1, there's different behaviors and different hyperparameter transfer depending on whether you use the SDE limit, which is alpha is 1/2, or what I would call the ODE limit, which is alpha equals 1. So in this paper, I don't know, they wanted to brand it complete P, but it's the neural ODE kind of limit, right? So that's the alpha is 1. That seems to transfer a lot better for transformer models, and it lets you also train like much deeper networks stably than what you could train with the SDE. Okay, so why? Why does this make sense? So let's say I don't have a linear layer, but each layer is some nonlinear function of the parameters for that block. To be stable, right, to have the right scale of update to the residual stream, I need everything to contribute 1 over L because the gradients that I accumulate are correlated across adjacent layers. So I need to think about the forward pass after an update as an average. So that means that actually implies a scale for my parameter updates. That implies that theta minus theta 0 has to be like L to this power. So if I'm in the neural SDE scaling, so if I'm in alpha as 1/2, that means I actually need to move theta minus theta 0 by 1 over square root of L. which means I'm actually entitled to linearize each block, right? So I'm not linearizing the whole network, so this is not like the NTK, but I am basically linearizing every block around its initial parameters. And there's one component that acts as this Brownian motion, these fluctuations we talked about, but then there's the learning update just comes from this, these linearized features. So locally, each block is linearized around its initial parameters. But then the neural ODE sort of retains all higher order nonlinear powers, but the Brownian motion disappears. But both of these things learn features in the sense that the hidden states change throughout training, but they, we say one is complete feature learning in the sense that it doesn't, no local subblock of the network can be linearized. So that's sort of a, anyways, okay. And then, okay, so you can apply the mean field theory ideas to try to analyze different kind of architectural limits of the transformer. One thing we tried first was the limit of infinite head size. So if you set things up so that you approach a stable, well-defined dynamical system, that implies you actually need this like 1/n key.query inner product. And what's interesting about this is that if you initialize everything randomly, as in h goes to infinity at fixed head size, the variance across attention heads, even through training, will actually go to 0. So all the attention heads end up doing the same thing. So even though you thought you had a multi-head attention model, as you keep scaling up in h, you're sort of going back to single-head attention. And then there's another option, which is you don't do mean field over the neurons in h, you do mean field over the attention heads. So you have an infinite number of heads, and there's a distribution over their activity patterns. So you have like a distribution over the attention matrices, basically. And whereas this first one does not always display monotonic improvements within h, and in fact, things get worse as you keep going sometimes, in many cases. This usually displays kind of monotonic improvements with increases in the size. And I think there's still some architectural questions. Can you change this so that you can have both, where you could scale in h and also maintain diversity? So I think that's still open, but okay. I mentioned there's this idea of MOEs. The idea is, instead of routing all my information densely through the entire network, I go through a sparse subset. So most of the compute that you actually spend in a transformer is through the NLP layers. So this was an attempt to reduce the amount of compute while retaining high dimensional kind of parameter space. So you try breaking up the MLP into a bunch of experts, and there's a gating or learnable gating or routing mechanism that maps your sort of token. So each token gets routed to like some subset K out of the E experts. And all of the kind of modern models are of this type. Okay, so how can we think about scaling up or down? Yeah.
Is each expert an MLP? Or?
So yeah, you can think about this whole thing as an MLP block, but it's like each of these is sort of a disconnected MLP. And then I'll write down the equation. Here, let's write it down. Okay, this is what we're doing. So this K is indexing which of the experts I'm looking at. This is like a gate, so there's a step function that's like a hard gate, and then there's this sigma. So I'm going to treat this, there's the gradients through this step function I'm going to treat as a no-op, because it's non-differentiable. So this is a no-op, but I'm going to do I'm allowed to differentiate through this sigma. And then, yeah, so each of these has like basically a 2-layer thing, and there's some hidden dimension in sub E, the expert width. That's the size of this hidden dimension. And the scale factors are chosen so that the response functions are well behaved in any of the limits that I consider. So in particular, as I take the residual stream dimension into infinity, I want things to be well defined. Okay. And so what are these P's? These P's are router scores. So I'm learning these, I'm going to try to train these weights R. And I need a 1/n factor actually for these router weights. And then there's also going to be a bias parameter for the router. So the router is going to have a bias. Okay, so the idea is I want, for a given token, to only activate the top K of the experts. So this Q star for a given token is a function of the tokens. It's defined implicitly so that the top K out of E experts are active. And okay, so different papers do different things. There's different strategies for encouraging what's called load balancing. So there's a concern about collapse, where all the tokens get routed to just some subset of these, or maybe one of the experts. You want basically tokens to be spread out evenly. So a lot of papers add auxiliary losses or penalties or regularization tricks. But then the entire network is sort of like coupling to this auxiliary loss. So like the attention layers are also getting feedback from whether your load balancing in layer 37 is happening or not, which seems bad. So we're using the strategy from some of the DeepSeek papers, actually, where there's a local rule for the bias that encourages basically load balancing. It's basically like the delta rule from basic like neuroscience learning theory. But basically it's encouraging how close is the actual observed fraction of the batch to k over e, which is the kind of typical or expected fraction. Okay. Okay, so here's what we argued. If you take the number of experts to infinity and the activated experts k to infinity together with the ratio constant, then you can actually do the DMFT, and you can actually say that there's a well-defined sort of scaling limit. That's a little bit weaker than what we would hope. Ideally, you'd want to have experts constant, or sorry, activated experts constant, experts diverging. I'll explain why that's hard. But the joint scaling condition under which you get a well-defined neural ODE limit is basically the width divided by the product of the expert width, the number of experts, and the depth has to kind of go to 0. And okay, suppose you do SGD. There's a 3-level DMFT that describes the dynamics. So at the residual stream level, there's the neurons and the kernels in the residual stream, like what we talked about earlier. There's a distribution over the expert states. So over, let's say, for example, the router variables. Okay, and then within that, what does top k mean? So because we're fixing kappa, which is k over e, top k corresponds to a quantile threshold. So suppose k over e is like 20%, then that means take the top 20% of the pk and use that as an indexing. So you're conditioning on the expert belonging to pk being greater than whatever. So, or you could imagine introducing a step function of the router variable pk being bigger than some q star, and q star is defined as a function of kappa. So the mean field theory works out well. So if you believe there's a mean field distribution, then this just is a quantile threshold, so it's very easy. And then lastly, there's a within expert distribution over the hidden neuron states. Okay, so there's 3 levels. And the neural network behavior, the macroscopic behavior, is again only given by averages over these 3 levels. So that's nice. And what's cool is you can get very kind of consistent dynamics across not just the width or the depth, but also across different FFN ratios. So the width of the expert divided by the total width, and also the total number of experts. And you're able to actually get hyperparameter transfer across all 4 scaling variables. For normal MLP, so this was actually kind of surprising. For normal MLPs, you don't have transfer over adjacent widths or like relative widths of different layers. It works here because of the residual structure and how we scaled things. Basically, you can also do some kind of like asymptotic analysis. So when you're very close, when you're in the neighborhood of the limit, you can quantify the kind of central limit theorem fluctuations in terms of width and depth and other things. Yep.
What happens if you take kappa to 0 at the end, which will be kind of the constant experts? Does it still perform normally? Or?
So yeah, in all these simulations, kappa was I think like 10 or 20%. We haven't tried taking kappa to 0. And, there's questions about whether. Also, people don't really take experts to infinity. The whole point is you just want to be able to like double it or quadruple it, and then have stable behavior. So there's a question about are we capturing the right thing? One issue we ran into was it's basically like more like a maximum or extreme value statistics, right? If I'm taking E large and let's say E are all the experts states are IID, so all the PKs are IID, then like the maximum will scale. Okay, if they're regular, if the distributions are regular, the max will scale like log E or something. So, and then you don't know that you have closure basically at the level of the mean field equation. So, this is what we could do at the moment, but probably the realistic thing is more like this extreme value statistics. Okay, I don't want to go into this too much, but there was an exotic thing that happens if you actually take the width over this ratio to a constant that's not 0, then you can have an SDE limit, but it's a complete feature learning SDE. So I thought from this other paper with Cerebrus that like only if you have the 1 over L scaling, you'll always get the ODE. But actually, there's joint scaling limits that maintain this complete feature learning property at infinite depth, but that are also SDEs. So that's kind of interesting. And there's a new paper from Liniak Shazat and colleagues that also has a similar thing that happens and just vanilla, so not an expert mixture of experts, but just a vanilla 2-layer res block kind of structure. So you can see that in our appendix, or also from his, what I think it's called ResNets of all shapes and sizes. Yeah, so in these papers, in both of these papers, the approximation errors are how close is the system to the neural ODE limit. But if you instead ask, hey, if I kept alpha star constant as I scaled up, then I'm asking how close I am to the SDE limit, and that really reduces the kind of approximation error. So my question is transfer better if you fix alpha star? So if you scale up across model sizes, keeping this aspect ratio constant. That's open, I don't know. But just to point out, this is, if you just do what people do in practice, that would be like the residual width diverges in, NE is linear in N, and the depth is linear in N. So this whole thing goes like 1 over N. So alpha star usually is going to zero, is zero, but I'm just saying there's this exotic thing that could happen. Okay, so what I wanted to get across is like there's this kind of general kind of framework for thinking about different kind of architectural scaling limits. It doesn't really tell you about the scaling laws, which are really about finite size effects. So how much does the finite model deviate from this like Platonic infinite width or infinite depth model? And for that, we don't have a complete theory of scaling laws. We have some kind of toy models at the moment, but to make practical decisions, I think we really should try to not just understand limits, but also kind of systematically try to understand their kind of the effects of finiteness. Okay. Here are just some experiments sort of that we did in this paper, but here, like, you can see finiteness is not a big deal in this like CFAR5M task on ResNets. So width 32 models are pretty close in behavior to width 512 models. And on like harder tasks like ImageNet or Wikitext, as you train, eventually like smaller models eventually start doing worse than bigger models, right? When things work, they work well. Like the mean field picture looks good. You have this kind of non-Gaussian but consistent single site density, and you have consistent kind of hidden feature kernels. That's nice. When things don't work well, early on in training, the error that you get is sort of consistent with central limit theorem fluctuations around the theory, which is what you'd get from a leading order kind of perturbative approximation around the mean field theory. But if you train for a long time, eventually the scaling law is sort of described by, it's better described by some other power law, right, which is reminiscent of the kind of like architectural and task-dependent scaling laws that people report. And this is just to show that these are not universal. So these are not always 1 over width. They depend on the architecture and the data set in this after a long amount of training. Okay. And yeah, we need to try to understand this in a theoretical model. So we've done some work on various kind of toy models of this, and I think Cengiz might discuss some of them. But the takeaways at a high level are infinite width and depth limits of neural networks can be described by some kind of stochastic process over each neuron. But the macroscopic behavior and the sort of prediction level behavior of the neural network is governed by like population averages. And this could be useful for things like hyperparameter transfer, trying to control the dynamics, making also, you can make small models look more like large models, right? If you have figured out a way of making this map work. So that's good for us because we can more closely mimic and reproduce. So there's a paper reproducing transformer instabilities through small scale proxies, this group at Google. And they're arguing that if you do these mu-p kind of things or these scaling tricks, then you can isolate different dependencies on the optimization pipeline and optimization stack in the small model before jumping to a bigger model. So it's also good for us as people who play with small models a lot. Okay, what's missing? So also, yeah, so this theory is sort of assuming, so it's just taking everything to infinity, all the architectural limits to infinity at fixed problem sizes. So input dimension is constant, batch size times steps is constant. So you don't start feeling these effects of different model sizes, right? You can't model the scaling laws with the theory that I described today. And ideally, we'd like to describe things at the kind of chinchilla scale where you're optimally trained, so parameters is of order data, or even beyond that. And yeah, this is still pretty open. Okay. And I'd just like to thank all my sort of wonderful co-authors over the years and various sources of funding. Yeah, thank you for your time.
other methods are very neuron-based methods. Just wonder, I didn't think about it so much before, that like when you actually train the networks that kind of works in this limit, like what is the behaviors you see in the neurons or in the activations, how stable they are, how
Yeah. I mean, it's very interesting. So I mean, if you simulate these with ReLU neurons and stuff,
Yeah.
you'll have changes in how sparse the activation patterns are. You can measure things like that. The SAE thing is interesting. So I don't know. So sparse like dictionary learning, I'm not sure how it plays with this, but things like PCA of the representation space, that's governed by the kernel. So if you know how the kernels are evolving, then I can integrate the equations up to time t and then look at the kernel after time t and do RSA kind of a analysis. How that connects to sparse dictionary learning, I think, is pretty open. I don't have a good understanding of that.
But do you see like if you when in linear network you have a very consistent kind of behaviors of neurons that you kind of sample different points in the Gaussian or something, but in the nonlinear networks, how consistent is the behavior?
Yeah, this still works very well. I mean, okay, so another problem with this that I should advertise is integrating these equations is hard on very large data sets. But on the small data sets that you can integrate the equations through, you can make it very nonlinear and it's still. I mean, so like let's look at the ReLU example again. Sorry, but like if you had a linear network, sorry. If you had a linear network, then all these densities would look Gaussian, like here. But these this lopsided thing where like there's more density that gets spread out to the right than on the left. This is due to the ReLU. Probably. No, so this H is pre-activation. So the pre-activation, because the weights changed in a way that depended on the ReLU gating, that actually made what should be a Gaussian under the NNGP or whatever, or the NTK, actually becomes non-Gaussians. But yeah, good question.
In your mixture of expert model, as the Q star that you have, is it usually constant? Will it make sense to have a schedule over that?
Oh, okay. So Q star is it's determined by kappa. It's a function of kappa for each data point. So if you set kappa is the ratio of k over e, like the.
So you want it exactly to have exact k, so you pick the Q star that.
Yeah. It's defined implicitly as just like so I have my density or whatever. So if I integrate the top kappa percentage, that needs to be equal to. That needs to be set by, so this cutoff needs to be Q star. So like the integral from Q star to infinity of the density rho of, what is it, P, dP has to equal my kappa variable. So this defines for each data point how, so I fix this. This is controlled by my limit of K over E. And then that determines uniquely a value of Q star. Yeah, but you're asking this variable, for example, can this have a schedule? Can you become sparser over time? It's a good question. I think you could become sparser over time. The biases would have to kind of dynamically update, I think, as well. But yeah, but
Do you usually keep it fixed?
we usually fix it. But yeah, it's a good point. Like you could start dense and then kind of prune over time. Yeah, become sparser. So by the end, because what you really care, you want sparsity for the end user, right? Like you don't really care if the initial bit of training was dense. It's, yeah, exactly, right. So you maybe the optimization landscape's a bit better if you allow kappa to be like large early in training, but then you want by the end to be like as sparse as possible or something. I think that should be, okay, I don't know this for sure, but I think that should be compatible. You should be able to do that, I think. That's a good question, yeah.
When you say OOD, is what you're saying that there is some concentration of the kernel at every layer, and then this kind of behaves continuously in the layer-to-layer sense?
So I mean, like if I viewed this as a discretization of some kind of stochastic process, so this thing has, so all these first order terms are independent across steps, so they look like independent increments. And they're of scale 1 over square root of L, which is like square root of my dt. So this is kind of like an Ito process. And then this though is actually, this is going to be of scale 1 over root L. And this is 1 over root L. So this is of scale 1 over L, but it's strongly correlated across steps. So this is more like a drift. So it's like there's a diffusion part and a drift part. In the what I call the ODE limit, there's just drift. There's no diffusion.
Yes. And so this means that at any layer there's a concentrating kernel, whereas in the SDE case there will not.
No, the kernel yeah. So the kernels, so the variances concentrate here. The variances are deterministic here in both cases. But the single neuron pre-activations across layers are either bouncy.
The kernel over the entire.
But the kernel is going to be smooth. The kernel will have it just like this example. So let's, where is it? So, right, so I have this rough process on the neuron level, the HI of tau. But in the kernel space, it's just a smooth ODE, right? It's this, if I took the limit of, right, this would just turn into a d tau of H is beta squared times, so it's a smooth ODE for the kernel, but the neurons are rough. Yeah.